So we will start the second hour of our presentation today. So Jilson, Siddiqui, over to you both.
All right, thanks, Catherine. This is Jilson speaking now. So let me push the slides to the audience. There you go. So let me start by thanking Sean for the introduction earlier, and thank you also for the Edmonton Geotechnical Society and Bentley for inviting me. We have lots of topics to talk about here on probabilistic modeling. I realize that I'm going to merely touch the surface of the subject. It's a very complex subject, but I'll try to give you just a very broad overview of what probabilistic modeling entails in slope stability analysis. So to give you first a general overview of the presentation, we're going to have, first I'll give you a background of probabilistic slope stability analysis. Then we'll discuss the statistical assessment of input parameters. Then we'll talk about what are the available probabilistic methods. Then we'll discuss briefly a comparison of these methods. And then I'll talk about the PLAXIS LE implementation of probabilistic methods for slope stability. So let's first start here with this brief background. There are statistics in probability. They can be applied in several ways in geotechnical engineering. There are numerous publications available describing these applications. The application of probabilistic analysis to data analysis, to experiment planning, to reliability analysis, and so on. So the motivation for probabilistic modeling comes from, for example, updates in design codes in several countries, the natural advancement in engineering practice, also from requirements from the insurance sector, so among other motivations. Fortunately, we as engineers, we have at our disposal multiple well-established approaches for bringing probability theory into geotechnical analysis. And these publications that I'm showing here in this slide, they just show a few of the major efforts in publishing books on this subject. So what is the benefit of doing probabilistic analysis of slope stability? Well, first we need to examine what a deterministic analysis means. A deterministic analysis is based on the factor of safety, of course, which is computed based on deterministic input parameters. The deterministic approach deals with a problem that is plagued with several sources of uncertainty. So it deals with that uncertainty by establishing a minimal acceptable factor of safety, right? So how do we know what is acceptable? Well, the design codes, they have established these values based on what seems to result in a frequency of unsatisfactory performance that falls within limits that we can consider as a society to be acceptable. So that's basically how we work when we are doing a deterministic analysis. Now, the problem is that there is a tendency to have in this situation, one recipe for design that needs to fit multiple scenarios that are not necessarily equivalent. So a probabilistic analysis, it addresses this situation because it allows us to compute the probability density function of the factor of safety. What this means is that multiple sources of uncertainty, they can be rigorously accounted for in this approach. So, for example, if you see this figure here, what you have is a situation where a slope with a relatively higher mean factor of safety of 1.5, and this slope could be actually could have actually a higher probability of failure when compared to this another slope here with a lower factor of safety. That is because the level of uncertainty can change for each slope condition. So in the end, the probabilistic approach introduces additional measures of slope stability that helps us introduce this variability, basically the probability of failure and the reliability index. So let's have a look very quickly here at the big picture. So how does probabilistic analysis of slope stability fits within a decision analysis process? So this is what this figure shows. So we have here several analysis steps and two main sets: the hazard assessment and this decision-making process. So on the left-hand side, what we see is that we need a model for quantifying our geohazard. So that's our slope stability model. And we have as an output our measure of slope hazard. So reliability index, probability of failure. So with that information, and this is what we are talking about in this presentation, we would bring that into consideration with more elements. We need to have an assessment of, oh, by the way, I mentioned probability of failure, but we, in certain situations, also need, for example, run-out distance. So with these informations, we can combine that with our assessment of the vulnerability of the structure, with a quantification then of risk levels that combines this vulnerability with the probability of failure. Then we can establish acceptable risk levels, and that's a major step here. Take that in combination with a collection of managing actions available, and then we can make our decision. So speaking about quantification of risk levels, this figure here by Professor Whitman shows that these levels, they depend on the consequence of failure. So therefore, structures whose failure have higher consequences are designed to have a lower probability of failure. And by the way, this figure also shows interesting comparisons against natural events, by the way. Well, in the end, the acceptable risk levels, they need to be established by society through appropriate regulation. I have here another example. This figure shows typical probabilities of failure. This one is from Becker, 1992. It shows these typical probability of failure values and how they compare against our typical design factors of safety for multiple structures. All right, so let's now discuss a little bit about what are the options for assessing our input parameters in a slope stability problem. So first, it is important to understand what are the sources of uncertainty for a soil. Well, the soil itself is a source of uncertainty. There is a geological process that renders the soil variable in space. So there is spatial variability. So this is considered inherent soil variability, which is characterized by, for example, a scale of fluctuation. Then we have uncertainty because of imperfections in our measurement procedures. This can be divided in data scatter, systematic error, which we actually don't want to deal with in our modeling. What we want to do is have adequate protocols in the laboratory to minimize the systematic errors. And of course, we can also have estimation model uncertainties related to estimation models. All these components, as described by Foon and Kohali, they add up, and in the end, we have a soil property uncertainty. So how can we define these uncertainties to use as input parameters in our slope stability model? Well, first option is the most difficult one. There's descriptive statistics, which means, well, the descriptive statistics is easy by itself. Which is difficult is to gather all the data required to have meaningful statistics. So basically we can evaluate our parameters, obtain mean values, variance, coefficients of variation, correlation coefficients between the multiple variables involved, and we can even evaluate spatial variability using the autocorrelation coefficient. For that, we require measurements, and measurements, they require time, and of course they require resources. So that's our first option. As I said, it's obviously not the most simple one, but we have other options. For example, there's the expert information option. We can use the 3 sigma rule, where we take the highest conceivable value of a parameter, its lowest conceivable value, and then we calculate its coefficient of variation, assuming that these values are really extreme values, so that we would have about 99.73% chance that it's between these values. This is quite difficult because no matter how experienced our expert is, he needs to be trained to adapt his way of thinking to select HCV and LCV values here that would be adequate. The other option is to use typical values. So this is based on the assumption that, well, once you know the variability of a certain parameter of a certain soil, it's not going to change by much in another site. So that's a huge assumption, of course, but I'd like to say that this is better than not doing probabilistic analysis. These are some reported values in the literature. This table is by no means complete. There's much more, but I would just point to 2 interesting pieces of information here that pertain to slope stability. The coefficient of variation of friction angle is between 7 and 12%, and there's more studies that have confirmed that. This is a typical range. Cohesion typically has a much higher range, and undrained shear strength even higher. So that means that in a slope stability problem, we want to take into consideration what is the impact of friction and cohesion or undrained shear strength, because that will allow us to know the level of uncertainty of our factor of safety, and it will depend largely on if the material is dominated by friction or cohesion, or if it's a situation where we have undrained shear strength. So, yeah, we have several options. I have another table here just showing you more typical values from the literature. This is for unsaturated soil parameters, like the air entry value, the slope of the hydraulic conductivity function. So there's publications that have shown us what are the typical values. This, by the way, is based on a very large database of soils, soil vision. So it is based on a big number of soils. It is a very good estimate for these coefficients of variation. And this is a correlation matrix for those same properties. So having discussed the background and how to obtain our input parameters, let us now talk briefly about what are the methods available for computing the reliability index and the probability of failure. The first method is Monte Carlo's method. Monte Carlo is very intuitive. Basically, the concept is and I'll read this out loud here. If you throw a fair dice many times, you will eventually come to the conclusion that there is a 1 in 6 chance of getting each possible outcome. That's Monte Carlo. We have a model for the factor of safety. Let's say we have a cohesion and friction angle that have a frequency distribution. Well, we throw the dice. We randomly generate values of cohesion and friction angle that follow their PDFs, their probability density functions. Of course, if you throw these dice large number of times. And then for each trial, we calculate the factor of safety. In the end, what we have n values of factor of safety. That means we're going to have a frequency distribution for the factor of safety. The main thing here with Monte Carlo is how many times we need to run the model. We typically require a very large number of trials. That means this is a very expensive option. But the model, the approach is very general, very robust, and it's therefore one of the most well-known and popular methods. By the way, there is one particular model approach called Latin hypercube, which is like Monte Carlo, but it's smarter in terms of it does what we call a stratified sampling. So it requires a lower number of evaluations of the factor of safety with equally good results. So it's a smarter Monte Carlo. And another approach is the Taylor series, which was originally proposed by Hahn and Shapiro in 1967. It is a method for obtaining the first few moments of your PDF. So here we are not obtaining the entire frequency distribution for the factor of safety. What we are going to do is we calculate the mean of the factor of safety and the variance, and then we assume a shape for the frequency distribution of the factor of safety, and then we can calculate our probability of failure. This can be done for one variable, but can be done for multiple variables using a multivariate Taylor series. The most popular version of this is what people know as first order, second moment. So here you see same equations as before, but we are throwing away higher order terms here of the Taylor series. This is a good moment to see that there is one big issue here. We require these derivatives. So the derivatives of the factor of safety they are not obtained using a continuous function, but we can do it using a numerical approach like this, by taking small steps for each variable and seeing its effect. So this is another possibility, the Taylor series method, which is basically more used in terms of the FOSM method. The final type of method that is widely known is the point estimate method. And this is actually a large family of methods. These are some of the main methods. It started mainly with Rosenbluth. This is the main referred method here. But Evans came first with other versions of the method. The point estimate method basically is a method for computing the moments, again, of the function of the frequency distribution of the factor of safety using specific points. That's why it's called point estimate. So we for example, we have cohesion as one input parameter. Well, if your cohesion has a mean value of 10 and a certain standard deviation, let's say 5, so that gives a 50% coefficient of variation, we're going to calculate the factor of safety for 10 minus 5, which is 5, and 10 minus 5, which is 15. So we add and subtract one standard deviation. And and then we multiply the result by a weight. This combination of points and weights was determined based on the matching of moments. Basically, it's a moment matching concept. So the problem with these methods is that they tend to require a lot of computations because they have redundant points, let's say. One way to try to resolve this issue is to have a smarter way of selecting these points. And this is where the APEM method comes. It's an alternative or hybrid point estimate method. We take the Taylor series and then we use Rosenbluth's, there's a typo here, sorry, to evaluate the required derivatives by the Taylor series. So it's a hybrid method, let's say, that combines both concepts. One interesting thing about the APEM is that the very same points that we use to calculate the factor of safety and then to calculate the probability of failure, well, those same points can be used to establish what we call a tornado diagram. A tornado diagram shows the impact of each input variable, of the variability of each input variable on the variability of the factor of safety. So there's each bar here, it gives, let's say, if this is for a confidence level of 80, it means there's a 10% chance that the factor of safety is lower than this value or higher than that value for this parameter. If we order the parameters according to the size, then we get what is the importance of each parameter. This is basically something that will give us the value of the information. For what parameters do we need to invest our resources in more investigation? It is really important and really useful. So just briefly talk about the comparison then of these methods. So Monte Carlo is the most flexible method by far. It accommodates different frequency distributions. It allows the consideration of correlated variables. It does not require any hypothesis regarding the factor of safety PDF. However, the computation requirement is extremely high. And so this is not something that we recommend for finite element transient problems. This is not advisable. The Taylor series method, well, it requires an assumption for the PDF of the factor of safety. The factor of safety must be linear function of the input random variables for our approximation for the derivatives. We can consider correlated variables in a more general Taylor series method, not on the popular FOSS method. The computation requirements is very low, of course, and so this is a very viable option for finite element and transient problems. The point estimate method is very similar to the Taylor series in terms of what we need to assume, the PDF for the factor of safety. We can consider correlated variables, but the computation requirements are much higher. And finally, the APEM, the hybrid method, it is basically a combination of the advantages of both the Taylor series and the point estimate method. This is just a plot here showing the number of evaluations required by Rosenbluth's point estimate method, the APEM and Taylor series. So obviously the APEM is much lower than Rosenbluth's. So to finish here, I'll just talk briefly about PLAXIS LE implementation of probabilistic methods. So there are three methods available, and they can be seen in this screenshot here. You have Monte Carlo, Latin hypercube, and then the APEM method. Associated with these methods, we have two options for the critical slip surface location, a fixed and a floating option. This means that if you select a fixed, it's going to find your critical slip surface using the mean values of each input parameter. and then it will retain that position in all the remaining trials for the computation of the probability of failure. With a floating approach, you let the slip surface loose. So it will search for the critical slip surface for each trial. It can also take into account spatial variability through random fields. And in terms of soil properties, the software has integration with SV soils, so you can store or use store your soils in a database and then retrieve the soils. You can select what soils you're going to consider as probabilistic, as uncertain, and then depending on the method, you're going to have more or less options in terms of your statistical distribution. Here's for Monte Carlo. You have normal, log normal, triangular, uniform, exponential, beta, gamma, and Poisson. So you have several options for your statistical description of your input parameters. And finally, in the implementation of these methods, we have several report options. So of course, you can see your histogram for your factor of safety. This is the case for when you do a Monte Carlo analysis. You can do this in a cumulative form also, and then the program automatically computes your mean value, your variance, your standard deviation, your reliability index, and your probability of failure. So I think I'm going to stop here on this slide, and I would like to invite Dr. Siddiqui to present to you some demos on probabilistic slope stability analysis. Over to you, Siddiqui.
Thank you very much, Professor Gilson. I'm going to start the video the demo for probabilistic analysis. Let's begin. Welcome everybody to demo of probabilistic methods in PLAXIS 3D LE. There will be 3 demo examples. The first one will be a 600-meter long embankment slope where slip surface is predefined by wedges. Second one will be a simple open pit where slip surfaces are defined by entry and exit method. And the third one will be a complex open pit with material volume meshes. Here slip surfaces are defined by grid and tangent method. This model demonstrates the use of multiple wedges to define the slip surface where slope topography is defined over 600-meter length. It is basically a embankment over the 600-meter. And its failure surface are defined by these wedges. As you can see that there are about 6-7 wedges which defines its failure surface. So failure surface is fully specified. So if we go into these model settings and see the model settings, we will be seeing that more clearly. That this is fully specified model, and the analysis will be done by the calculation method only GLE, general limit equilibrium method, and one directional method in 3D, and all other parameters are set as default parameters, and we have chosen here the probabilistic analysis that we like to show. And as you can see here that remaining other parameters fixed. You can see the Monte Carlo method we are using, but there are other methods like Latin hypercube and alternate point estimation method. So in the Monte Carlo method, this number of samples is very, very important. It relates to many other features of Monte Carlo. Let's see what are the other things that we can find out in this number of samples. The number of samples actually relates the desired level of confidence, that is 0 to 100%, and normal standard deviation, that we can put it here, and number of variables, we can put it here, and number of current variables are here. So you can see that if we change anything, it's going to change. So if we put something like, here, 0.8 level of confidence, you can see that here it is reduced to 4,751. And if it is 0.8, then 80% confidence level, we need to change this one else also. Then the number of Monte Carlo comes down to 1074 trials. You can see that this has been explained by Professor Gilson in his slide, that there is a formula for calculating the number of trials in Monte Carlo, which is related to the variable, number of variables, and a error term, which is not shown here, and this standard deviation and level of confidence. So having said that, we are going to use a fixed number, which is 1000. So the level of confidence will be a little bit lower than 80%, but that's okay. Otherwise, it exponentially grows up, and it can take very, very long time. There's other two selections, that critical slip surface locations, whether it's fixed or floating. So initially, the analysis tries to get a deterministic solution of the embankment, and using that deterministic solution as a fixed is try to vary the material parameters according to the material model. I will show you those material models a little bit later. And then from that variation, you try to get the variation of the result as factor of safety, and try to run 1000 times and try to calculate the number of failures among those 1000, and calculate the probability of failure, number of failed samples and total number of samples multiplied by 100. There are other options like floating. In case of floating, what it does, it varies everything. I mean, for each random parameters from the material model, I try to calculate the location of the slip surface. So the number of trials, grows exponentially, which takes a very, very long time, even for faster computer. So let's see some of the model parameters that we can see here. So you can see that there are two metal are placed here. One is clay, another is just material. And we can see these material models, if we click here, you can see that cohesion and phi and unity, and these three are actually defines that metal parameter. And here also the same thing. This is the weak plane, so there is no unit weight. And when you go to the probabilistic method, we can add these, probabilistic method, we can add C, phi, and then these are added. You can see that here it is, C is usually we put in a log normal distribution. You see there are different types of distribution over here. So for clay, we take a log normal distribution, and for phi, we usually take a normal distribution. Usually we vary, C standard distribution, standard deviation, we vary about, 30% to 50%, and phi we try to vary about 10%. So you can see that there is a logic behind why we take, log normal for C, and because we do not allow any of these parameters to become negative. But if we take a normal distribution, there is always a chance that it can become negative, at any point of taking random samples. On the other hand, if we give a log normal, there is no way that the parameter can be negative. So that's the main reason that we give these kind of distributions here. So we have this parameter set up. So I tweak these parameters in such a way that we have a probability of failure of something like 4 to 5%. So once this is set and we have our model, parameters, I mean the main method of calculations and the probability we turn on, and number of samples and generous seed, and these slip surface location are fixed, we are good to go for the analysis. Nothing else we need to set at this moment. So once material properties are probabilistically set, and this is also set, we can go here and start running the model, just clicking this, and if we just save and continue, it will start to run. So I'm just showing here the results of the run that we made, And you can see the results are, factor of safety is 1.12, 1.12, and we have the probability of failure is 4.2. And I have pre-calculated results. Let's go there and show you the result. You can see here that we have a probability of failure 4.8% as I adjusted the parameters to get this value, and we can see the failed surface here. If we can see a little bit better, I think you already know from Marina and Maria's presentation that I think cleared you all this. I think you can see that how it failed, and that's a very nice feature that we can see it here. And we can see the probabilistic failures parameter output here. So you can see the factor of safety here. This is the variation of the factor of safety with this density function. That the deterministic result is around here, 1.10126 here. And these are the distribution. So this is the most probable one, but these are also have some probability, but lower probability of getting to these values. Say what is the distribution of C? You can see this is the distribution of cohesion, so normal distribution. You can see log normal distribution, and this is phi. So this is the weak plane C, weak plane phi. So there are many other options that we can try with. This is the density PDF function. We can have cumulative function. So this is the probability, cumulative probability of C of being 32. This is the probability directly is given. And this is the density function, and we have the summary. We can get to histogram also. So this is a nice plot, histogram. What does it mean? It means that the normal distribution, the green one is the expected one. That really we are trying to follow this, normal distribution for clay phi. But the blue one that actually we are getting from the Monte Carlo random generation of these parameters. And in this bin, you can make it a little bit denser if you want. Get a better understanding how this Monte Carlo works. You can see this is random value, so sometimes it's going above this expected curve, sometimes below expected curve. So as the number of sampling grows, so it will really follow this curve. I mean, if you take, say, 1 million samples, then you will see exactly this flowing. That is actually said in the probability, that is the theory of large numbers. When you toss something, very large numbers, so it will follow, the distribution that is supposed to be. So we can see that the factor of safety is here. This is, this is the actual factor of safety we are getting, from Monte Carlo simulation. So from here we can understand that what is the probability of failure that can happen here. So again, it is the same model. That is, the multiple wedges is defined here for the slip surface failure, and it is ranging over 600 meters long in this direction. So let's see the model. We defined another, that is Latin hypercube. Now we'll be doing Latin hypercube, and it has a definite pattern of choosing the random samples, but at a regular interval. So this takes really short time for the sample of metal parameter generation, and we can get the same result as the Monte Carlo with less number of samples. But anyway, here we using the fixed number of iteration as Monte Carlo 1000. That means that latent hypercube will give a better result, than the Monte Carlo with the same number of samples. And other things, I think I didn't change anything. The same things we'll be doing only for the fixed analysis. We go back and we can simply run it the same way. I can save and run. So you can see here that the model ran perfectly. It took about 23 minutes. Here we simply can go to the result section and see the results. So you can see that the surface is almost same and probability of failure is 4.2%, very similar to Monte Carlo. And let's see some of the results here. Latent hypercube. So the distribution here, you can see that the distribution of factor of safety is pretty similar to Monte Carlo, but it is really faster than Monte Carlo with a similar confidence level of result. So we can see that the distribution of parameters cohesion of clay with, say, want to see the histogram. And say a little bit denser histogram looks better. Now it's interesting to see that unlike the distribution by Monte Carlo, here this is log normal. You can see a little bit skewed in this direction, and it is not much, above this line, mostly following this line pretty closely. So this is a much better way of sampling the latent hypercube. It divides this, into regular intervals, and then within the interval, it tries to get randomly the parameter it needs for this probabilistic analysis. And we can see the similar behavior for clay. It is normal, so it is pretty normal distribution, not like the log normal one, little bit skewed on the left. So this explains, the fast solution by this latent hypercube technique. Other things remaining same, I think we can go for a scatter plot and see, how this is scattered here. I mean, this is the phi parameter, so we can see the other parameters as well. You can see the factor of safety is in this range. So this is the histogram plot for factor of safety. So in the histogram, it is not very different from the Monte Carlo. Yeah, its combination maybe, there's some failures. You can see that this is below this, all failed, and that is, shown here in this result, that 4.2%. It is the same model, that 600-meter long embankment model. So nothing is changed. We can go to the settings and we can select this APM, that is alternate point estimation method, which is a very powerful method. I think Professor Gilson already explained to you that that the expected factor of safety is expanded in a Taylor series for the different parameters and geometry, and from there it can fit the model very quickly using the 2-point or 3-point method. And yeah, that's it. Once it is calibrated, it can calculate the probability of failure very fast. So other things, everything is set, so we can run this one as it is pretty fast and it is fully specified. So hopefully it will not take much time to show you how it can calculate the result. So you can see that it's fully specified probability analysis. only it needs 17 trials. And this 17 is calculated internally from the APEM method. So it is done. You can see that pretty same value of probability of failure. So we can go to the results, and we can go the APM results, and similarly you can see this density plots, and most important thing here, we can see another thing, that the tornado diagram means that which parameter is the most important one and which has the most effective sensitivity to the analysis are shown here. So you can see here that is deterministic analysis, means that it is the probabilistic analysis definitely, but the parameters are arranged, in such a way that, say, it is calculating for this parameter, the clay phi, so this is varied probabilistically and all the others are deterministic. So it has, you can see the maximum effect for this one. So this means that this is 10th percentile, this is 90%, so it is within that it is varying. And when we are calculating the effect of this one, symmetrical phi, so same thing we are doing, we are varying this one probabilistically, but all other we are keeping deterministic, so we can see the effect of this one. So from this analysis we can understand that clay phi of the clay has the largest effect, so the factor of safety really varies, for this variation of this parameter, so it is the largest effect on this slope. We can see also the probabilistic plot of this tornado diagram, and it is just opposite of the deterministic one. Here you see that the same thing, the phi of clay has the largest effect, but here we are varying, all, we are just keeping this one, we are not varying. So that is the way that we are calculating this one, and this is showing the same thing, that it has the largest effect, and all other have a similar effect, not a effect that we should take care. So this example is used to illustrate the analysis of a three-dimensional slope stability model for the slope of an open pit. This is a complex open pit. The slip direction is taken as parallel to the x-axis, and similar to the earlier example, we can go to the settings and you can find out that how we set it up. This is a 3D slip surface analysis with entry and exit. So you will see that we have this entry and exit defined, so that it can search for the deterministic failure surface, and starting from there for the probabilistic method. And the probability we have just chosen here the Monte Carlo method, and already I explained that although this number depends on different values of level of confidence, standard deviation, number of variables, but we have chosen for practicality about 1000 to use the time of calculation. And I think other things as a fixed analysis means that it deterministically determines the failure surface and varies all the probabilistic parameters on that to find out the range of probability of failure. And we are not doing any floating, it is disabled here due to the large expectation of calculation time. So having said that, we can see here the entry and exit setup that we have already chosen to give this entry exit data. It is already there, so we don't need to change anything. Let's run it here. It will take some time, but not that long, so I have chosen to show it for you. See that almost 1 minute to each run. It is done, and the value is 1.8, you see. And you can see that some of the results is very clear here. This is the failure. You can see that with some heat maps. And we can go and see the Monte Carlo results. That is the reflection of the parameters here. So we can see the histogram as before. We can make it 50 and maybe go for cohesion. You see that Monte Carlo has, this kind of distribution. Now we'll be using the same model for Latin hypercube. So everything is same. So let's explain a little bit of the material models here. You can see that there are 5 different soils, and there is a weak layer, and the probabilistic material parameters are same as deterministic. Just C are defined as log normal, and phi are defined as normal distribution. And C is varying, little bit larger variation than the phi. I think here it is similar, but 10%. But usually we vary about 30 to 50% C and phi for 10%. So let's go back to our setting, and we can see that everything is same. Just we change here to Latin hypercube. That's it, nothing we need to change, and we can simply run it and see that how it goes. And you can see that probability of failure is about 2.3%. There's some variation, I think, due to the number of trials. So here you can see that this is the failure surface. Let's see some of the results. So I think it is exactly the same analysis, so nothing changed. We can simply see the histogram, and you can see here 50 to make it a little bit better. And you can see here the distribution is much smoother here due to the Latin hypercube. It try to divide equally throughout its range and try to find out the random value within that slice. So it's nice and very clean distribution. So expected and actual distribution are pretty close in this. So Latin hypercube is really used in the probabilistic analysis in many cases, many different kinds of analysis. It's a very popular method. It is the same model as before. It's the complex open pit model. So we like to just show you quickly the material model didn't change at all. It's same as the metal parameter distributions that we used in the previous 2 analysis for this open pit. And we have the settings, model settings, that everything is same as before. We just have AP method, alternate point estimation method fixed here. This is a pretty fast method, so let's run it and see that how fast it is. You can see it's just blazing fast. Yeah, before I click anything, it's done. And we can see the results is pretty similar. So it's okay. And we can see some results here. APM. So like all of the results, here in the APM, we emphasize on the tornado diagram, which is very fascinating. It will give you the more additional information about how different materials actually influences the variability of your factor of safety. or how much variation of each parameter can have on the failure of factor of safety, or getting the factor of safety in the particular range. So this is two kinds of analysis of tornado diagram. One is deterministic, one is probabilistic. For deterministic, you see the top line here is showing a range of 10 percentile to 90 percentile of the variation, and this is for phi of weak layer. So we can see that, I mean, this really affecting your factor of safety very much. And what does it mean? It means that, I mean, in this analysis, this is varying. All other parameters are kept deterministic or average value, and we have this variation. For each of it, we make it fixed, varying for a range, and then others we are fixing to see the effect on factor of safety. In this way, the whole diagram is calculated. And on the other hand, the probabilistic, see, this is just opposite of what we did with the probabilistic deterministic method. That for each one, you know, this is the average value for running the probabilistic method, and all other parameters are varied to see what is the effect of this parameter. So you can see that again the weak layer phi has an effect like this one, you know. You can see that all others has a similar effect compared to this one, you know, when we invert the analysis compared to the probabilistic method. So we find out that definitely that the weak layer, the phi of weak layer, has larger effect on the factor of safety of this open pit. And then we can change or, you know, tweak this, you know, this weak layer to optimize our slope or make the slope much stabler, or we can check against any kinds of future probability of failure. So this is the last example that we like to show you. This is an example of open pit slope stability model. It makes use of material volume measures to define volumes of rock intrusions and ores. It also uses bedding guides to define a series of rock beddings and ALM materials to model the difference in rock mass and bedding strength, the mix of which is determined by the sliding mass base geometry. Let's see the material parameters that we have here. We say that most of the materials are wake brown, you know, materials. That is the, you know, protrusion of the ores that is shown here as you know, MVM meshes, and others are, there is a base rock mass, the base ALM, you know, this anisotropic one, which is shown here, and you can see the, and others you can see here. These are the models, and we tweaked a little bit to get our probabilistic model, and mostly we use, you know, we vary the UCS value, the uniaxial compressive strength values, you know, adjusted for a reasonable value of failures that we can show you here as an example. And for grid and tangent, we define the grid and tangent in such a way that it curves maximum number of, you know, materials here. You can see that this is the grid, and the tangent is such a plane here that it cuts most of the materials, and also the, you know, bedding plane anisotropy is captured by this analysis. And other things, I think you already know that we are using a method, you know, as GLE, and probability we are taking this one. Monte Carlo, and for Monte Carlo, you know that a number of trials are decided by a formula, but we are fixing it 1000 to closely to a 80% confidence level. So let's run it. Some of the MDMs are going out of this boundary of analysis, but it's okay. it automatically cancels those parts. So now you can see that it is using the grid and tangent method. It is trying to get the deterministic solutions. So once this is done, it will go for the GLE, and it will take some time to complete this GLE analysis. So you can see here the run is completed now. So we can see the results. So as you can see, the results are here. Now this is the failure, so it's a little bit obscured by other planes. Let's blow it up a little bit, so we'll be able to see here. So it's pretty nice that you can see that the failure plane is not very ellipsoidal, because it has the weak plane, ALM model, so that captured the, that anisotropic planes as well. And let's see the other results that I'd like to say about the Monte Carlo. It is same as before. I think this is the summary result factor of safety curves, that you can see that this part is actually failure. It's the failure probability of that came out to be, this is 6.2%. For different materials, you can see the results. You can see the Wake-Brown UCS variations. This is the green one is the expected variation, and the blue one is actually we got from Monte Carlo. As usual, Monte Carlo shows some, overshoot or undershoot at a larger amount. This is the same model, but we'll do it for Latin hypercube. Only thing we need to set up here as Latin hypercube. That's it, nothing else. Everything remains same. So we go and we run the model again, and it will take almost a similar kind of time. So we have just finished our calculation. So let's see the result. The result is, you can see the probability failure is 6.513%. Let's see some of the exciting results. So the failure surface is the same surface, and so let's see some of the Latin hypercube probabilistic results that we can see. Is the factor of safety, and we can see the histogram for factor of safety parameters. You can see the different parameters are here. And for Latin hypercube, as I showed in the earlier example as well, that the curve, the expected and the outcome parameter distribution are almost same. It's very smooth. So the green one is the expected one, and the blue one is the histogram from this Latin hypercube sampling, and they are almost same and pretty smooth. So this is the same model. We will be checking for APEM model, that is the alternate point estimation method. Everything remaining same, so we can just say that the grid and tangent, the research method, and other things are same. The metal model are same, and the slip surface are given by grid and tangent are defined already. So we can simply run it. Run will be pretty fast, I guess. So again, it is searching for the deterministic values of probabilistic deterministic values of failure. So once this is done, I think we can automatically program will check for the APEM method, which is pretty fast. So now it is doing the probabilistic method, you can see. So it is done. Probability method is pretty fast, and the probability of failure is 4.883%. And we can check this failure surface. We can check that whether it is same as before or something different, because that method is pretty, very fast. So how come it remains same? So let's check it out. Yeah, it is same. You can see. Yeah, the surface is, not ellipsoidal. So that confirms that it is taking care of the anisotropy inside the bedding planes. So let's see the other results of APEM. And the most interesting result of APEM is the tornado diagram. And it's nice tornado diagram. You can see that for the rye, wake brown is the most influencing materials that are HY, wake brown UCS, and then CAD layers are also influencing, and then base ALM means anisotropy. The base materials will also have some effect, and others are not. So I will explain this. This means that deterministic means that this is not. This is varied only, and these are all average values or deterministic values are used, and subsequently all are calculated like that. On the other hand, in the probabilistic method of tornado diagram calculation, the opposite way, we can see the same results in a reverse way, that rye has the effect on this probabilistic failure, because and when it is only varied, so it has an impact on the factor of safety, you can see, compared to the others. That's it. If you have any questions and any queries, you can write it down there, and then it will come back to you. Professor Gilson is here. He can answer, of any questions about this demonstration or anything about his presentation as well. Thank you very much.
Thank you,
Professor
Siddiqui,
Gilson.
and thank you, Jilson.
Great.
Thanks, Siddiqui. Great presentation.